Welcome to day 10 of the 2023 Advent of Code. So today's problem is this year's first real graph theory problem. So it's on a grid, and we have a bunch of characters, and these are the pipes that we have to deal with. So we have vertical, horizontal, and all four 90-degree bends, and then we have ground with no pipes, and finally we have the starting position marked as S. There's a pipe here, but the map will not show us what shape the pipe is, so we have to infer that. Unfortunately, it's not too difficult. Based on the animal scurrying, we know that the pipe that contains the animal is one large continuous loop. So here's an example of a loop. If the animal entered the loop at the northwest corner, then we would have an S at the top left. And so in this diagram, we can tell that S is blocking an F bend because we can see how the adjacent pipes connect. And so we're guaranteed implicitly that S will only connect to two pipes. Unfortunately, there are also a bunch of random leftover pipes that aren't connected. Based on this diagram, we can still figure out which pipes form the main loop, because we see that this S only can possibly connect to these two, as these two pipes face in the wrong directions, and then we can just keep pathfinding. We can see that this pipe can't go up because it doesn't join up, this pipe can't go right, and so we end up with a complete loop like so. Okay, so this is a slightly more complex loop, which goes around a bunch of zigzags, and then here are a bunch of extra non-loop tiles put in. We want to get out ahead of the animal, so we want to find the tile that's the farthest away from the starting position. And since the animal's in the pipe, it doesn't make sense to measure by the direct distance. Instead, we want to find the longest distance along the loop, regardless of which way around the loop it goes. So basically the point at the opposite end of the loop. And so in the first example here, we see that S is at distance 0 because it's already there, and the J here is at distance 4. It is the furthest away, as anything closer would either be closer on this side or on this side. And so in this more complex loop, the furthest point would be this 7 here. It's exactly halfway between, across from the S around the loop. So starting at S, how many steps along the loop does it take to get to the farthest point? So basically, given the length of the loop, we essentially just divide it by 2. I think you might have to adjust for 1 off, but that's basically the idea. So let's first grab the input. So the input is just going to be a massive grid. So we can take a grid, we can do open 0.read.splitlines, and that will give us our grid as our input. And now we want to find the starting position. So let's call it SR and SC for the starting row and column coordinates. So for row and row in enumerate grid, for C and character in enumerate row, this basically scans through the entire grid, and if the character is equal to S, then we set starting row and starting column and exit the loop. This syntax here is an interesting construct that I run into a decent amount. Basically, if this loop breaks, then it will skip the else and break. If this doesn't break, then it'll go into the else and continue skipping this break. So else continue break is basically a way to propagate a break up the loop. Since, as far as I know at least, Python doesn't have loop labeling, so you can't break out of an outer loop. Unless they added that somewhat recently. I haven't caught up fully with new Python features. Okay. So now that we have our starting row and column position, let me first grab the correct test case. Let's take this slightly more complex one. We get a starting position of row 2 and column 0, which is correct here. So now we basically want to pathfind through the entire thing. And so in order to do that, we'll implement a breadth first flood. So let me pull out the whiteboard. Essentially, the concept of a breadth first fill is we start at some point, or maybe multiple points, and then we try every single next position we could go to. If it's valid, we add that to our queue of things to look for. If it's invalid, we just ignore it. And so, after we've scanned everything, our queue now contains these two values. Then we try every possible place that this can go to. If we've already seen it, so we need to track a list of nodes we've seen, then we skip it. So let's say we get that, for example. And then after we're done with this one, we don't go to these two yet, we go to the next one in the queue. So that's the idea of breadth first. Basically, we start from a point and then we scan going out in parallel instead of going along one path to the end and then tracing back and checking other paths. And so let's say this arrives at the same point that we've already added to our queue. We don't add it again, so we avoid duplicating work this way. So to do that, we'll need a queue, and the easiest way to get that in Python is from collections import deque. A deque is similar to a queue. A queue basically is a data structure where you can put items in one end and take them out the other. A deque allows you to do that to both sides. There is a queue module, a module in Python, but as far as I know, it's a bit harder to use or not as efficient or something like that. Either way, deque is useful because it can be used as a queue, a stack, or just as the deque itself if you sometimes need that. Okay, so now that we have the starting position, we can keep a scene set, which will start as just the starting coordinates, and then we'll also keep a queue, like so. So now we want to do our pathfinding. So while the queue is not empty, we still have more things to look for. And so if so the current row and column position is queue.popleft, which gets the leftmost element out of the queue. And now we can start our pathfinding. So the current character is grid at r at c, like so. And so now we can just manually check each of the 4 directions. So in order to go up, we must not be at row 0. And we must be in a position that is able to go up. So if the character is in either the starting position or one of the pipes that is able to go up. So S, vertical pipe, and also J and L. And the character that we are trying to go to must also be able to receive upward motion. So it must be pipe, F, or 7. Let's say 7 or F. If these conditions are true, then we can go up. So we will say if, the other condition is if r-1c is not already seen. If it's already seen, then we want to skip it so we don't duplicate work. Then we will add it to our scene set and also append it to the queue. So queue.append will append an item to the right. There's also append left. If you want to use a deque as a queue, you just have to make sure that your pop and append operations are coming from opposite sides. It does not matter if you do pop left and append or pop and append left. There is no difference. Now we check downward motion. So if we're not in the last row and our current position is able to move down and the position below us is able to accept downward motion, accept downward motion, and we haven't already seen it, then we do the same thing. Similar thing for leftward motion. If the the column is greater than 0, and we're able to move left, and the position to our left is able to be moved to from the right, LF, and we haven't already visited this node, and finally we check motion to the right. So there's probably a bit more efficient of a way of doing this, but this was just the most straightforward method I could think of. LF and grid rc+1 in dash or j or 7, and rc+1 is not seen. Then we add rc+1 to scene and to the queue. So now at the end, if we print out scene, this should give us the coordinates of every point along the pipe. So we get 1, 2, 3, 4. We get 16 values, which does make sense. And so I think you can just print the length divided by 2. Yeah, that will give you the correct answer, because scene contains all of the items in the pipe, and so we just need to find the furthest point, and so it's just the point that's halfway across, because if we go in either direction from the halfway point, then it would be shorter to get there on one side or the other. So that's for part 1. Part 2 is a bit more complicated. We want to find the area enclosed within the loop, because maybe because we notice that the animal never emerges, maybe it's looking for a nest that is within the area enclosed by the loop. So we need to find anything that's considered inside the loop. So in this case, only these 4 points are inside the loop. This is considered outside because there's a path that leads to the outside. And in fact, there doesn't even need to be a full tile path to the outside. So this is where things get annoying, because this would be easy by just starting from any outside point and flooding the entire thing to see what the outside nodes are. You can also squeeze between pipes like so. And so these nodes do not have a full tile path to the outside, but they still need to be considered. And here's a much more complicated example. So something we can do for checking if something is inside or outside the loop is by checking how many times it crosses the path of the loop. So in this case, this inside point, if we go to the left, we see that it crosses the pipe once. If we go to the right, we see that it crosses the pipe 3 times. If we go up, we can consider this F pipe L as not crossing the pipe, instead it's just riding along it. And so it only crosses the pipe once here, and it only crosses the pipe below it once. So in all directions, the number of times it crosses is odd. Now, if we consider something like this, for example, we can also consider this as just riding along the pipe, so it crosses 0 times. To the left, it crosses twice, to the right, it crosses twice, and above, it crosses twice. So those are even, and so this is outside. But is this just a coincidence, or does it actually work? Let's look at a bit more complicated of an example. Let's look at this isolated eye here. So would we consider this riding along the pipe? So why did I'm going to say this is no. This counts as crossing the pipe, and so this is just one crossing, and so it's considered inside. But why do I consider this as crossing the pipe and this as not? And the reason for it is actually very simple. This is the point that we're looking at. This is the outside world. And if we have a pipe that looks like this, then we can get around it. But if we have a pipe that looks like this, then we need to cross through it. And so that's the distinction. If the 2 ends of the pipe point in opposite directions, then we are crossing it. If the 2 ends point in the same direction, then we can just ride along it. So that's the distinction. Going up, we see that these point in the same direction, so we skip it, and it crosses the pipe once. Going left, these both go up, so we skip it. 1, 2, skip, skip. 3, 4, and 5. So that's 5 crossings to the left, still an odd number. Going down, these 2 are skipped, and we cross once. And going up, sorry, we already did that. And so it is indeed an odd number in all directions. And I'll leave the proof as a little bit of an exercise, but that's basically how we're going to do this. Now, we can optimize this a bit more, although it's totally unnecessary. I did not optimize this during the contest, I'm just doing it now for fun. Instead of checking every single point and scanning, we can start at the left edge and just do a horizontal scan and mark all invalid nodes. And then we can do a vertical scan from the top and repeat the same. And we don't need to check from the right actually, because the number of crossings to the left and the right has to add up to an even number. That's necessarily true. Before we proceed though, there's one important thing we need to do. We need to figure out what S is, because if we leave it as S, then it doesn't let us know how we should handle it when we're doing our scanning. This is not too complicated of an issue to deal with. We can just track, so we can keep a set of possible S values, so possible S values, or we can just call it maybe S. We can start it out as just all of the possible values. And then each time we make a traversal from S, we can say if the character is equal to S, then it must be one of these three values, because the reason we allow all s's here is because it's a placeholder for any of these values. So we can say maybe s is the intersection of the current set and these three. And we can basically repeat the same thing for each of these. So instead of pipe JL, it's pipe 7F here. Instead of pipe 7F, it's here dash J7. And here it's dash LF. And so at the end, we should assert that the length of maybe S is equal to 1. And then we can just let S equal the sole value. Here we can see that in our test case, this must be an F. And if we try it on our real input, it must be a pipe, which if we look here, that is correct. We can only go up or down from here. So this S is a vertical pipe. Okay, with that out of the way, let's replace it within the grid. So grid equals row.replace the literal S with the value of S for each row. And so now we have our grid, but with the S value turned into what it really is. Okay, so now let's keep a set of points that we are considering invalid, so what's considered outside. So let's first do our horizontal scan. So for each row, we're going to look at each character and take it case by case. So for character in row, we have a couple of possibilities for the character. So let's define a couple of values. So whether or not it's currently within is going to start out as false. And whether or not we're riding along a pipe is going to start out as false as well. This value actually isn't really needed, but I'll keep it for some assertions just to make sure our input looks correct. And finally, we'll need to keep track of which direction it's facing. So up is going to start out as none. We'll make it true or false once we actually meet something that we're riding along. Okay. And just to make things a bit simpler, let's also get rid of anything in the grid that isn't within the loop. So let's replace all of the garbage pipes with just dots. So we can do that by saying for our row in grid, enumerate grid. We do for C car in enumerate row. And so now we can do if RC is in scene, so if it's part of the loop, let's rename it to loop actually. I need to fix the syntax first. If it's in the loop, then it'll be the character itself. If it's not in the loop, we'll replace it with a dot. So let me print out the grid just so we see what that ends up turning it into. Oh, right, because I forgot to turn this back into a string. So that's what our grid looks like now. So we have replaced this L, for example, this one here, with a dot because it wasn't part of the main loop. If we replace for the main input, we see that it simplifies things out a lot. So that's what our loop looks like now. I wouldn't say a lot, sorry. But it does get rid of a bunch of garbage pipe values. And the reason this is nice for us is just because now we don't need to check if the character's in the loop before processing. Because when we do this horizontal sweep, we need to make sure we're only looking at pipes that are actually relevant. And this is because crossing over pipes that aren't in the loop doesn't affect the status of whether we're inside or outside. Okay, so if the character is a vertical pipe, then we've crossed. So we're going to first assert that we're not riding along a pipe, because that would mean that we would run into a horizontal pipe like this, which should be invalid. And we're also going to assert that up is equal to none, because we shouldn't have an up-down if we're not riding along a pipe. Actually, let's get rid of the riding value and just use up is none as to assert that value. And so we're going to flip within, so within equals not within. And that's all we need to do for a vertical pipe. Otherwise, if the character is equal to a horizontal pipe, we assert that up is not none, which means that we are indeed riding along a pipe and we did hit something, either an L or a... We did hit one of the 4 special characters first. And in this case, we don't do anything to within. Otherwise, if the character is equal to either of... Since we're sweeping to the right, if it's equal to either L or F, then we should first assert that up is none, because we shouldn't be riding along a pipe when we reach them. And then we're going to say up is equal to CH equals L. So if the character is L, then we're facing up. If it's F, then we're not facing up. And otherwise, if the character is equal to 7 or J, then we're going to assert that up is not none. And then we're going to set up equal to none. But before we do that, we first need to check whether or not we've flipped over. So when we cross over the end of a horizontal pipe, then if it flipped directions, so if up, if the character is not equal to J if up else 7, what that means is if we're facing up, we expect a J. If we're facing down, we expect a 7. And if it's not equal to that, then we're going to flip whether or not we're within the loop. And so at the end here, we should do else raise new runtime, raise runtime error, unexpected character horizontal, and print out the character. So we shouldn't run into this case because this should be the only possible outcome. And then at the very end here, we're just going to mark this point as invalid if it's invalid. So let's, I forgot to do this earlier, but let's enumerate our values. And if we're not within the loop, then we're going to add our current R and C values to within. Oh, yeah, I forgot to deal with the dot. If it's a dot, we just do nothing. And so this is what it tells us are all of the outside values. So let's print this out into a grid to make it a bit nicer. For R in range length grid, for C in range length row, we print out a # if our C is within the outside set, otherwise a dot, and we end it with empty space so that we can print these all on one line. And then at the end we can print out a spare new line. So this is what we get. This is what it says is considered outside. So let's subtract the loop so it's a bit clearer to see what's going on here. So it says that these 3 values, this top corner is outside, which is correct. These 2 values are outside, which is correct. And these 3 values are outside, which is correct. It just occurred to me I should switch my test case because that one doesn't help us. Let's look at this one. So it tells us that all of these values are outside, which is all correct. So that's just the horizontal part of the scan. I am curious now, actually, if that just gives us our answer. Okay, let's assume it gives us our answer, and if not, we'll do the column-wise scan. So now that we know which values are in the loop and which values are outside, it's a simple matter of just subtracting the sum of those two from the total. So we can just do print the number of rows, so length grid, times the number of columns, so the length of the first row, minus the length of all values that are either outside the loop or part of the loop. This actually does give us our answer. I thought we would have to do a vertical scan, but I guess this is sufficient. If this doesn't work for you though, then maybe this is just a coincidence, but I kind of doubt it for an input size this large that it would be a complete coincidence. But if you need to do a column scan, one neat trick you can do for transposing the grid is you can zip star grid. So what this star does is it essentially passes each value of grid in as its own argument. So if we print a list like this, you'll see that it's output as a list normally, but if we use the star, which is known as the splat operator, it's the same as calling it with each of the elements in the list as an argument. And zip takes multiple arrays and goes through them column-wise. And so what this does is it passes each row of grid into zip as a separate argument, and so zip goes through each of the columns. And then you can just convert that to a list, or if you're just if you're just looping, you can just do for C call in enumerate zip grid, and then just do within is false, left is none, for R character in enumerate call, etc. It's the same idea basically. All you would need to do is you would need to change up all of these characters to match what we're doing vertically. But yeah, I actually was not sure that doing it just a horizontal scan would work, but it seems that it does, so that would be a solution for part 2. There are some other interesting methods as well. We can perhaps explore some of these on a later video, but I have heard a couple of ideas such as adding half coordinates to allow you to squeeze through pipes like this when flood filling, and marking any point to the left or right of an item in the loop as outside, and then flood filling from both the left coordinates and the right coordinates, and just taking the intersection or something along those lines. In any case, thank you for watching, and I hope you enjoyed.